Good morning, Brigitte.
Guten Morgen. Schon lange nicht mehr gesehen.
Ja.
Oder gehört.
Ja.
Gehört.
Wie ist das jetzt eigentlich? Wird es jetzt über den Livestream übertragen?
Ja, wir haben gerade den Livestream angeschaltet. Wir checken das gerade. Ne?
Okay.
Ja, wir hatten eben erklärt, man braucht einen Premium-Account von Zoom, den kann man direkt heraus in Livestream generieren aus dem Premium-Account. Aber Horst hat schon eingekauft. Ja?
Ah.
Und das testen wir heute, ob das denn auch stabil läuft. Ja?
Okay, so I think we are now live on YouTube. There's at least 44 people watching us now also. Good morning, everybody.
Good morning, Guido. Huh? And we see now the Zoom projection on YouTube, yes? Huh?
Yes, I think we just see the video faces.
Mm-hmm.
And as soon as our speaker arrives, he will take the stage.
Yes.
So Guido, if you want to say something, you have to unmute. Your microphone is muted.
Thank you.
Yes.
Good morning, everybody.
Good morning, Guido. Huh? So again, during the talk, I will mute everybody except the speaker. Yes. Don't worry.
Mention that me and Duran are here. Can you mention to Mario that me and Duran are here? Okay.
Okay.
Nitin and Duran just arrived.
Yes, we have. I see them. Huh? So we have also some audience. Huh?
Yeah.
Not just a virtual audience.
Please keep 2 meter distance. Huh?
Yeah.
And not more than 5, huh?
Not more than 5. At the moment we are 3.
Yeah.
Yes.
In a big room.
We must make one of these YouTube songs.
Come a bit closer. Otherwise you don't like it.
So the point is that not everybody from the Institute should join this chat, or
no, at the moment we are still fine. We are only 26 people and we have a capacity of 100. Huh?
Okay. So should I invite my group to join, or should I not invite them to join?
No, I would prefer that we look at the stream. Huh?
Yeah. Okay, good. All right.
But it would be good to test the capacity of Zoom. Yeah. Maybe we can.
Okay. I mean, maybe we can do it in the discussion. Huh?
Yes,
yeah.
Okay. If Horst takes the responsibility.
You know, I have big shoulders, so I gladly do that.
You're also in California, so you know we
virtually.
Yeah, that's where I would be if we didn't have the Corona thing.
Yeah.
Mm-hmm.
Yeah. So
we
are still
in outer space. I mean, that's even wilder, you know.
So I think we are set now, except we are still waiting for the speaker. Huh? So.
We see Matthias also. Yeah, okay.
Mm-hmm.
eine ganz doofe Frage. Wo kommt dann dieser Vortrag? Ist der jetzt im Zoom oder dann in YouTube?
Der Vortragende hat gerade, ist gerade im Warteraum. Er kommt gleich rein.
Ah, okay.
Hello.
Hello.
Oh.
Good morning, Anatole. I was just writing you an email, but I didn't send it away. Okay.
I got an email that we were meeting in this other place. Was that wrong or?
No.
For the afternoon.
In the afternoon, yeah. This is...
In the afternoon. I'm sorry. Okay. I thought also in the morning. Okay.
Okay. Now we are set. Time. It's up. And the speaker has shown up. So it's like in the usual meeting, but today nothing is usual. Okay, welcome to everybody. So my name is Professor Mario Ruhm from Institute of Nanotechnology and Institute of Quantum Materials and Technology in Karlsruhe and Institut de Physique et de Chimie de Matériaux, IPCMS, de Université de Strasbourg. I welcome everybody to the presentation of Professor Anatole von Lilienfeld from the University of Basel. With maybe some words, this is an experiment. This is the very first time we are trying to give this kind of presentation, which is something like a remote presentation. Anatole is sitting in Basel. Huh? So this meeting was planned to take place in Karlsruhe in the seminar room. Under Matthias, the seminar room, we are now 3 people, so a real audience. But on top of the seminar room, we will have also audience at the KIT, Karlsruhe Institute of Technology. There will be Zoom members, participants as well. There is a YouTube live stream. And we will have also distributed this live stream and also Zoom at the University of Strasbourg. Yes. And this you will see by the names among the Zoom members. This is a mixed audience today, physics and chemistry, but also Strasbourg and Karlsruhe. And we have also the seminar room. So for the discussion afterwards, only the Zoom members will have the opportunity to give questions, and of course also the people in the seminar room. The people from the live stream, which are following by live stream, will have to send email, maybe to Shannon or to me, and we will try to convey this question to Anatole. It has to be also said, this meeting is planned within the frame of a Eucor European Campus project, Eucor seed money project about exactly quantum machine learning. And today we had planned in Karlsruhe the kickoff. Shannon is the initiator of this project. And Karlsruhe Institute of Technology and University of Basel and University of Strasbourg are members of this project, and we would like to foster this topic in future along the Upper Rhine River Valley. I have to thank, before I start to introduce Anatole, Matthias Hettler in Karlsruhe, and also Shannon for taking care for all the technical details that we are able to make this presentation today. And for the Zoom members, I will mute now everybody, and maybe I think it might be also a good idea to gain some bandwidth if we switch off the video. Huh? So I mute I mute everybody now except Anatole, who has to speak. So our speaker, can you hear me? Yes. Professor Anatole von Lilienfeld from the University of Basel. So Anatole started to study chemistry at different places in Leipzig, in Strasbourg and ETH and in Cambridge. You see, this was already a tour of Europe, obviously, with studies. He had also projects already during his studies, obviously diploma projects with Professor Quack and Professor, in Cambridge it was Professor Handy. And when for the PhD, he joined the group of Professor Rötlisberger, and obviously he made also the move from ETH to EPFL in Lausanne in Switzerland, where he also got his PhD. He was still very mobile in the period afterwards. The postdoc period, he touched places like UCLA, Los Angeles, in New York University in New York, obviously, Max Planck Institute in Mainz, Sandia Lab, University of Chicago, and Argonne laboratories, all very premium places, of course. And before he came back to Europe, to take a SNF, Swiss National Foundation of assistant professorship at the University of Basel, where he continued in different positions from 2013 to 2016. When he moved shortly to Free University of Brussels, to come back in 2016 to University of Basel, where I see now faculty member of the Institute of Physical Chemistry and the Department of Chemistry as associate professor. And having introduced Anatole in this with his CV, I would give him the stage now for his presentation, Quantum Machine Learning. This is exactly also the title of this Eucor seed money project I mentioned before. And we are happy to learn a lot about this very interesting topic. Please, Anatole, share your presentation.
Thank you, Mario. Hello, everyone. It's a pleasure to be here. I already have given Zoom presentations, but it's every time a little bit of an adventure. So let me try to share my screen now. And just to verify, does everybody see this now?
In my
segment.
Yes, you see it?
See only, okay, now getting better.
Now
Good.
It's getting better. It was creased, huh? But now it's
Okay.
fine, Anatole. Huh? Now we have a full
All right.
picture. Huh?
All right. Thank you then. So this is my cover slide. You see on the top the URL of our group. We do quantum machine learning, and I'll be talking about that later on. And we also do alchemy, computational alchemy. And the goal of our efforts is really to get a better grasp of chemical compound space. I hope to, even though I focus mostly on the machine learning aspects of our work, I hope to convey more details of what we do and why and how this works in this presentation. So to motivate this work, I should briefly mention the huge size and importance of chemical compound space. So compound space is that space of all possible materials. So that is much more than what has been made so far and characterized and studied. There are many more combinations, and one obvious area where this matters is, of course, drug design. But also materials design efforts, they move in the space of all possible compounds. And so we'd like to better understand how the space is structured, what relationships there are, and how we can rapidly move through the space and exploit relationships to identify interesting materials or molecules. So this slide shows screenshots from two papers. One was a Nature Insight in 2004 in Nature, with a whole set of interesting perspective articles on chemical space by various prominent figures in the drug discovery community, including, for instance, Christopher Lipinski from the Rule of Five. On the right-hand side, you see a more recent review by Moulard in Nature 2017, where actually some comparison was included of data sets that are known. So here you see the number of compounds, and these are the approved drugs. The PubChem library is a well-established library of compounds that are known. Also the Zinc library. And then there's a virtual library, the GDB17, which was created by organic chemists in an effort to enumerate all possible organic molecules that would be stable and interesting for bio applications. Now this bar here on the right is, it corresponds to 10 to the 60, and this is a conservative estimate of possible medium-sized organic chemistry molecules. So we're not even mentioning yet inorganic systems. We don't mention solids, materials, and so on. It's just these medium-sized molecules. And obviously, this is a space which is gigantic, and we are not able to screen such a space at all to find interesting systems. So it's really paramount to be able to exploit all possible knowledge of relationships throughout this space. And this is where we combine quantum mechanics kind of view with machine learning, artificial intelligence approaches in order to more rapidly go through this space. Now, of course, compound space, the letters of this of the possible compounds that make up this world, the alphabet consists of the periodic table, and this is well known. But you should be aware that the ordering, for instance, in the periodic table is actually quite arbitrary. There's no law in physics which tells you that you should order this way. And if you remember from high school chemistry, it's ordered by principal quantum numbers. So this is how the groups emerge, but you could choose other ordering as well. And here are alternative schemes, less well known. On the left-hand side, you see some spiral arrangements. These are not wrong. This is just another way to depict it. And a particularly useful alternative way of depicting the periodic table was provided by David Pettifor in the 80s, where he introduced what he called the Mendeleev numbering. And you see these lines on the right-hand side that run through the periodic table. And if you follow these lines, if you order elements like this, a very nice property emerges, namely that you see this on the right-hand side, that the formation energy of a material made up of the element following the order of the Mendeleev's number, so Pettifor's ordering scheme, if that element forms a carbide or nitride, you see a very nice linear trend in the formation energy. And you would not get this trend if you just plotted things according to the ordering in the periodic table, right? And so this is just by means of a simple reordering, hidden correlation throughout compound space emerges, right? And this is an example of what we are after. And just to show that this is not research that stopped in the 80s, there's also this screenshot here from a paper from 2016 with Hardy Gross and Miguel Marquez, who published a modified and adaptation of this. Now, of course, the Petitfort scale or numbering scheme is a low-dimensional representation of compound space, and compound space is much higher dimensional. So for some properties and some materials classes, it's actually possible to exploit such a one-dimensional effective trend, but in general, it's a much higher dimensional problem. And so these are non-obvious things when it comes, for example, to molecules. And what you see here is a figure from one of our papers where we use neural nets to train a cross-chemical compound space on various electronic structure properties. And these structure properties include the energy, the homo eigenvalues, LUMO eigenvalues, electron affinities, etc., at various levels of theory as well. And basically in every panel you see here one property scattered against the other. Every point in this panel corresponds to one molecule, one organic molecule. In every panel you have roughly 7,000 results shown for 7,000 molecules for which we obtained these electronic properties. When I was still at Argonne, we used the supercomputer there to calculate them. And now, of course, it's clear that many properties seem completely uncorrelated, right? At first, if you just plot the scatter plot, but there are some relations between them, right? They are not independent. They are all, more specifically, they are all expectation values of the same differential equation, which is Schrödinger's equation, right? So using the same wave function, they correspond to integrals over different operators. There should be a way to extract this relationship. And this is not obvious, of course, but we can use machine learning. And here's an example for how this can be done, also from this paper. So we trained neural nets with multiple properties, so multi-input, multi-output neural nets. And if you do that, you can then make a prediction on, for example, homo eigenvalues and energies, total energies. While seemingly there's no correlation, if you plot the principal component, the first and the second one, with the largest eigenvalues of in this coefficient space of the neural net, you see that in 4 dimensions, where now the third dimension is the energy, and the fourth dimension is the color coding, which corresponds to the homo eigenvalue, you see that a nice correlation emerges, right? And we can easily read off the trend through a chemical compound space. And so this is sort of what we are after, right? We try to exploit the power of statistical learning in combination with quantum mechanics, and with the ultimate goal to get a better grasp on materials design. We have a little review, my collaborators and I, Klaus Müller and Alex Tkachenko, Klaus Müller is at the TU Berlin and Alex Tkachenko is at University of Luxembourg. We just had a review on this idea, accepted in Nature Chemistry Reviews. It's already on the archive, so you can already look at it. And the idea is then that we have a chemical space where patterns re-emerge, right? And this is, of course, well known in materials and chemical sciences that the behavior of the same atoms in different chemical environments are not unrelated, and that's what we are trying to extract, right? And a more formal flow chart is shown here on the right, how you could do this. So if you select a bunch of molecules, you can solve their quantum mechanical equations, you can get their properties, and you can train a machine learning model on this. And then you can use this machine learning model to scan larger spaces using some optimization algorithm, for instance, on a multi-objective penalty. Use genetic algorithms or Monte Carlo sampling methods, doesn't matter, but you use the machine learning models to evaluate this objective function. And then based on this outcome, you select the next set of compounds. And if you do this iteratively, you're closing the loop on materials compound design and doing this from first principles, so at least in principle without any empiricism. Now, chemical space from this first principles point of view is really quite readily defined. And in particular, what I'm showing here is Hohenberg-Kohn, the Kohn-Sham equation of one electron I. And this is the Kohn-Sham operator. And in this Kohn-Sham operator, you have, of course, the kinetic part, but you also have the Kohn-Sham potential, which explicitly encodes the external potential. And it is the external potential which contains the specific nuclear charges Z, so that defines the stoichiometry of your system, and the structure, so the coordinates of each atom in your system, right? And so this is how in quantum mechanics and quantum chemistry, how the compound space is encoded. And we can see because of that, that the dimensionality of the problem is 4n, so 3 for the real space coordinates of your atoms, and a 4th dimension for the nuclear charge, plus 1, where the 1 stands for the number of electrons you distribute over your system, right? So this is the formal scaling of chemical compound space from first principle. You could add another dimension if you wanted to deal with certain electronic states, right? So then you'd need another index. But other than that, that is the formal problem. So in this sense, any compound, let's say the molecule N2, the most abundant one in the atmosphere, would correspond to a point in that high dimensional space. And quantum mechanics allows us to map that point to any set of observables. And so that's really the power of quantum mechanics, and that's why we like it so much. You can navigate that space smoothly, and numerical demonstration for this is given here, coming from this paper here with Stan Fiers, a collaborator of mine. So what you see here is the electronic energy of your system, so the potential electronic energy of your system as a function of interatomic distance. For instance, in N2, you would get this red line. And if you change nuclear charges, you can move to CO or BF, right? And this space is very smooth, and so we can interpolate in this space. And that's something we do when we use computational alchemy. We smoothly interpolate systems of varying structure and composition. But this also means that we can build regression models and interpolations in these spaces, right? So as long as you have the smoothness requirements fulfilled by your equations, there should be nothing that prevents you from building very rigorous and well-working regressors on such in such high-dimensional spaces. So what usually then happens in quantum chemistry is that we have a whole set of approximations we make when solving Schrödinger's equation. So nobody solves Schrödinger's equation exactly. So in practice, you need to make some approximation to actually be able to numerically solve it. And the more severe these approximations, the less computational cost you should expect. So for force fields, semi-empirical methods, Hartree-Fock, so mean field kind of approaches, perturbation approaches, explicitly correlated approaches, you have to invest increasingly more compute time. But in exchange, you can expect a better predictive power. So in comparison to experiment, your error should come down, at least in principle. Now, do not please quote me on these numbers. These are just rough estimates of errors you would make in energy predictions and rough estimates on time requirements you need in terms of CPU investments. Now, this is sort of the landscape a computational chemist would have to navigate on a daily basis. Now, if you succeed in pulling down points from this diagonal and pulling them below, for instance, if your mean field approach can be improved as it is done by density functional theory, then for the same investment, you get more accuracy, and that represents a major advancement in theory. And so not surprisingly, Walter Kohn and also John Popel, they obtained the Nobel Prize in 98 in chemistry for their work pushing this theory and making them more accurate while not having to sacrifice more CPU time. Now, our goal is to try to get into the lower left-hand corner by combining correlations among different molecules, right? So in this more traditional view, which you see here, you would solve Schrödinger's equation one system after the other, right? One system at the time. And you would not make use of previous solutions of Schrödinger's equation, which you already calculated before. And our hope is that by using alchemy or by using machine learning, that we can accelerate the solution of Schrödinger's equation, the approximate solution of Schrödinger's equation, dramatically, effectively get much closer to this goal post. So these are the two approaches we pursue in alchemy. Basically, computational alchemy is quite well established in atomistic simulation. It's nothing esoteric. The idea is basically a perturbation approach. So suppose you solve Schrödinger's equation for this black dot here. The question would be, how can you, with using perturbation theory, how can you predict points that are nearby, and not only on the same potential energy surface of one material, but also for a new material, right? And so these predictions, this is what we call alchemy. Machine learning actually corresponds to trying to answer the reverse question. So suppose that you have solved all the empty symbols numerically. You can now ask, what is the statistically most likely answer for this black dot here, right? So what's the Bayesian, so given all these other data, what is the most probable estimate of an expectation value for a missing data point, right? And this is also known as supervised learning. And Wapnick and others in the 90s really formalized this, and this is what we are trying to apply and exploit for this application in chemical compound space. So this brings me now to quantum machine learning and also to this Eucor effort, and I'm really excited to be a part of this because it's not only about what I just described, but how I defined QML in our sort of research, but it's also about a complementary way of viewing QML, and that is depicted actually on the Wikipedia homepage of quantum machine learning. You can see this. There's this distinction between the type of algorithm you're using and the type of data you're dealing with, right? And in some sense, we are using classical machine learning on quantum data. So this QC box is to what we typically do. But quantum machine learning is also well defined in the sense that you want to use a quantum algorithm on classical data. That's when you apply it, for instance, to fluid dynamics or such problems, or classical, let's say, image recognition. But you could also apply it on quantum data, and it's this QQ box, which I find the most interesting thing, and it's certainly something I'd be very happy to collaborate on. So why do we call our kind of problem QML, right? So this application of classical machine learning to quantum data. Actually, this is something very much in line with traditional terminology in our community. When you talk about quantum mechanics, you're actually using equations from mechanics, applying them to quantum problems. When you talk about quantum Monte Carlo, what people do is classical Monte Carlo moves on propagators for quantum objects, namely the electrons, or the coefficient space of your wave functions. We also have something called ab initio molecular dynamics, also known as first principles molecular dynamics, or also known as quantum molecular dynamics. This is classical Newtonian molecular dynamics, but you use forces on your atoms that were calculated on the fly from quantum mechanics. So this idea that you use a classical algorithm on a quantum object is very much in line with how we traditionally have the nomenclature in atomistic simulation communities. So for that reason, we like to call our applications of machine learning quantum machine learning. You should be aware of the fact that, for instance, in the computational pharmaceutical sciences, where people try to discover new drug candidates on a computer, they also have been using machine learning for a very long time. Now, this also helps us to distinguish ourselves from these, it's noted here, the quantitative structure activity relationship or quantitative structure property relationship, where they also use machine learning to explore chemical compound space. Now, we have this added quantum component to that. This is why we are different, and this means also that we solve quantum problems with machine learning. And a friend of mine, Sergei Kalinin, he is very jealous of us. He's an experimentalist, and he says theorists know everything. I would object to that, but his point is that as theoreticians, we are in the privilege. We have the privilege that we know our system. We know our Hamiltonians usually. Unless you're dealing with some inverse problem, but in principle, at least for solving Schrödinger's equation, you have to know your Hamiltonian, and so by that we already know everything, right? So we have perfect control. So this means really, and this is also how we distinguish ourselves from many unsupervised machine learning problems. We have a causal relationship of some material, some system towards its properties, right? And we can get these properties as observers, as expectation values of the solution from Schrödinger's equation. So this is a very straightforward problem in machine learning, that you learn this map of input to output, and all you need is many examples. And it should therefore come to no surprise that actually machine learning in the atomistic simulation, so in the physics and quantum world, has a long tradition. And one of the earliest papers is from the 90s with Bobby Sumter and Bill Noyd. Bobby Sumter now being a director at Oak Ridge National Lab in Tennessee, where they already in the 90s used neural nets to fit potential energy surfaces. And Herschel Rabbits in Princeton in the 90s then used kernel methods to do something similar. And then in the 2000 things with increasing frequency, you find contributions by many important scientists in the field. Nowadays, Jörg Behler in Göttingen and Gabor Szani in Cambridge belong to the most prominent representative researchers trying to use machine learning to train on quantum data and to predict quantum results or quantum quality estimates of energies. Now, what distinguishes the work in my lab a little bit from, or maybe more importantly, from these precedented works is that we really have a focus on training the machines across compound space in order to be able to predict new properties of new compounds. While these more traditional ways of using machine learning and atomistic simulation were really geared towards training and predicting on any given compound. So in order to, for instance, run extended molecular dynamics to collect the statistical mechanical averages to converge them faster when you run MD. So the goal and the setup is quite distinct in that. And this is work that started in 2011, which was the year when I organized a 3-month program at the Institute of Pure and Applied Mathematics at UCLA. And the theme of this program was navigating chemical compound space for bio and materials design. And at that program, Klaus Müller, whom I mentioned earlier, my long-term collaborator, Alex Tkachenko, and Matthias Rupp, at the time a postdoc with Klaus, they participated, and I approached Klaus with this question: why can't, if you can learn images across image space, why can't we learn molecules and materials across compound space? And Klaus said, of course we can, and all we should do is start off by using, for instance, typical regressor such as the kernel-rich regression. And you see the expression for this here. So your model of some property, some estimation of a property of some material M is nothing else than linear expansion in training molecules I. Every training compound has a weight alpha I, and this weight gets multiplied with a similarity measure between your material, your training material I, and your query material M. This similarity measure is what's known as a nonlinear kernel function, and this is the kernel trick. You move the nonlinearity into this kernel function, and you still have a linear regression problem. So the training steps consists of calculating the weight vector for each training instance by inverting the kernel matrix between, so the similarity matrix between all your training instances, which gets multiplied by the reference property values. So the training amounts basically to the inversion of this kernel matrix within kernel-rich regression. Now, note that we are assuming here negligible numerical noise. So you can introduce some noise level to make this matrix to avoid that it's ill-conditioned and to ensure numerical stability. So I'm omitting these kind of details in this talk. The picture that emerges here is that you have to define representations, which are denoted here as M, symbol M, which represent your system very much corresponds to chemical space, as I told you about earlier. And in between these points, they span a simplex, a high-dimensional simplex in the high-dimensional compound space. between these points, you have similarity measures, right? So you know the distances, and when you now wish to predict a new compound, you're basically interpolating in this high-dimensional space. It should be clear that as you increase the data density of your reference systems, that interpolation should improve in its predictive power, right? And so this was something that is really important. In order to do this, though, we had to define a representation. And this was basically then my job to come up with this. And what I proposed first was this Coulomb matrix. The Coulomb matrix is a simple representation which records the nuclear repulsion between all atoms as off-diagonal elements. So for something like ethanol, it would look like this. And so the entries, they scale the further apart the atoms, the smaller the entry, the smaller the nuclear charges, the smaller the entry. On the diagonal, you would place something like an energy estimate of the free atom, such that if your system decomposes and all atoms dissociate, only the diagonal elements would survive. And if you take the trace of that diagonal, then you have an energy estimate of the stoichiometry of all your atoms, right? So this was something after trying many alternative things. This is extremely easy to generate. It's similar to the adjacency matrix. You can, if you know the coordinates of your system and the composition, as you should know it when solving Schrödinger's equation as well. So this was really important to us, that we are using the same input variables as you would commonly use to set up a quantum calculation on your system. So using the simple representation, we could then train the machine by inverting this matrix. And in particular, we were interested to see how does the error of the prediction decay as we increase that matrix, as we increase our training set. And this is then what we found. The error decays quite rapidly. So we could see that you see here the error on the energy of the system decaying as a function of training set size systematically. And at 5,000 molecules or so, you would get an error of 10 kcal per mole, which is a typical error for a GGA functional. And so you have to realize that a GGA functional calculation at the time was still half a CPU hour or so for such a molecule, while a machine learning prediction is a millisecond. So this got us really excited, and so I think this is the promise of this quantum machine learning when we apply it throughout compound space. Now, a typical question is, what about the overfitting? And we think that the traditional view of how we see overfitting is being altered by going through to this kernel-rich regression, the so-called also non-parametric machine learning models. And I try to explain that now. So when traditionally you would view a situation like this, where you have some data and a rigid functional form to fit, that would be underfitting. This would look just right, and this looks like overfitting. Now, to properly define this, though, you should use your test error and your training error. And your training error obviously should come always further down the more data you have. So the more in non-parametric models, the model complexity grows with data size. And if you test, then at some point your test error should go up again. So that will be this case, right? And so the best thing is the optimum, the minimum in your test error. Now, in our case, the picture is a little bit different, because we are not really regressing in the traditional sense that you would have to compromise with some model, just as shown here in red. Rather, we are interpolating in these black dots, and we want to go through every data point that we provide in terms of training, right? So it doesn't make sense for us to actually say, if we know this is a true data point, then we know the true model should go through this, right? And so the picture is rather like this one on the bottom right here, where you have certain data points, you need to go through them, and that's shown by the blue dashed line here. And then in between, you know also that the confidence interval should be much larger, right? While on your data point, it should be really close to 0. And that's the picture, I think, that best captures this approach. And it's also obvious then that as you increase the data density, that confidence interval should also shrink. And so what basically then happens to your test and train learning curves is that if you monitor your error as a function of training set size, our training error is always 0 or very close to 0. Right? We don't have really noise. Our numerical noise is many orders of magnitude smaller than the actual signal. So this error on your training data should correspond roughly to the numerical noise in your data. And then your test error must come down systematically as you increase your data density. And this is different from traditional fitting, which I learned in my undergraduate studies, which you would use in experimental sciences or such, where you would typically have the train and the test errors get together and then converge towards an optimum. And no matter how much more data you add, you will not improve anymore. And to me, this also is the distinguishing marker for what we call machine learning. Machine learning means your model should become better with increasing data sets size. And so this is a crucial test for me. If if you really have a machine learning model, your learning curve should keep on coming down. And in particular, Wapnick showed this in the 90s for kernel-rich regression. He gave proof that your out-of-sample prediction error must decay inversely with training set size n. And also our friend Klaus Müller, actually in the 90s, he showed that the same holds for neural nets. So this is not something specific to one regressor or the other. Any machine learning should really obey this, this rule. And this is just the leading error term that decays like this. But from that follows that if you plotted things on a log-log curve, you should really get a linear decay in the error. And so very similar to the traditional quantum chemistry picture view, what we now have is that your error must come down as you increase your training set size. Now, what we have here is no longer CPU time, but rather number of training instances. And then once you trained, you can make a prediction at that accuracy, but your prediction is in millisecond speed, right? So this is how I think we can approach this left-hand corner, basically shifting. It's not a free lunch. We shift the cost up front. And once you have that data, you can train a model on it, and that model is so fast. Now, the acquisition of the data can still be very costly. The training of the model can still be very costly. What's important is that the speed up which you have in the prediction of a new instance, that one is very fast, so you can use it to rapidly explore that vast space of possible materials. Now, I have a couple of examples I'd like to tell you about of papers where we have been working on these learning curves, and we were trying to get their offset down to improve their slope and to avoid a learning curve like this, which for small training set sizes might look favorable, but then you actually realize it's not really a machine learning model. It levels off to above some desirable threshold. In 2018, I also wrote a little tutorial essay on this in Angewandte, where you can read more on this. So let me tell you about the role of the representation now. When we started out with the Coulomb matrix in 2012, your learning curves so we have a data set of organic molecules called QM9. This is how the learning curve would look like. We subsequently had an adapted version of the Coulomb matrix just as a bagged vector representation, which improved things, and you see an improvement in offset. So one question which you encounter frequently is how to improve your representation for machine learning. And when you ask this question to a machine learning expert, they typically say you should include more physics. Now that's not always obvious how to include more physics. What can be much easier is to remove some physics. And so this is what you see here on the left-hand side. In blue, you see the 1/r decay we have in the Coulomb matrix, arguing that the interactions between atoms must decay with distance. Now you can say it would be less physical if they grew with distance. And here you see in red, they grow linearly. On black, they grow quadratically with distance, certainly less physical. Now, what happens to the learning curves? Do they deteriorate as you would expect? And so this is the learning curve, again, on this QM9 data set using the Coulomb matrix. Sure enough, you make the distance dependence, you turn it around, you make it less physical, your learning curve goes up. If you make it quadratic, it goes even further up. So if you neglect the physics in your property, you can still learn, but your learning is less favorable, less data efficient if you do so. So the more of the physics we can include, the more we can make use of our expertise, the more data efficient this machine learning model will be. So going down the other way by playing with this exponent here, we see that the learning curves actually converge for the exponent range 4, 6, 8, and where 6 is of course the Lennard-Jones dissociative tail exponent, so the dispersion from Fritz London, the dispersion tail, and for 10 it comes up again, so it looks like a hypersurface where the optimum is around 4, 6, or 8. So based on this, we thought, well, the best representation we can have would include all the possible physics we know of, and that's encoded in a force field. And so that's something we tried, and sure enough, if you use a force field for bonds, angles, and torsion, you get a systematic improvement. And once you include the angles and the torsions explicitly, you outperform Coulomb matrix or Bob. And this is for an enthalpy, so it's the energy stored in the bonds of the molecules. But this also works for other properties, heat capacities, dipole moments, polarizability. You always find as you include more physics, things improve. And this was shown now for a subset of molecules from this QM9, having this stoichiometry, but we can also do it for all of the QM9 molecules. There's 134,000 molecules, and we still see the same kind of trend. So quite overwhelming numerical evidence that this sort of reasoning should be true. So this model with the force field, we call it the bonds, angles, and so on. So the Baumel force field results on this curve into this learning curve. And we worked on some additional improvements, and I'm going to skip a couple of slides now because I spent too much time in the beginning. But we with people from Google, we started to work together to find a better representation, and this was the best representation we found with them. It was simply a histogram of bond distances, angles, and torsional and molecules. And this is something we call HDAT, the histogram of distances, angles, and dihedrals. You see this in red here. We then in my group with Felix Faber, who used to be a PhD student in my group, he just recently graduated and moved on with a postdoctoral fellowship to University of Cambridge. Felix, in his PhD, worked on generalizing these ideas, combining the histograms with the physics, and we came up with what we call now the FCHL representation. It's a systematic expansions in the interatomic body terms. The one body term is basically a Gaussian in the periodic table, where you place it in period and group of the periodic table. And this allows us also to interpolate between different stoichiometries. And due to the Gaussian nature, here you see the pairwise distributions, and here you see three body distributions. Due to the Gaussian nature, we can easily get analytical expressions for all the distances, and so the representation is quite efficient. And what you see now here in black is this FCHL representation. You compare this to the Coulomb matrix, right? This reflects nearly 10 years of work in this field, from 2011 to 2020 now. And this is how much you can gain, right, in terms of accuracy. Or if you compare here, many orders of magnitudes in data size we improved if you move along the horizontal line here. Other groups in the field started developing methods and tested them on this data set as well. So we have here the SOAP representation from Garbocciani and Michele Ceriotti. You have some constant size descriptor from Carnegie Mellon. Google also contributed in message passing neural net here. So the most recent overview on this is shown here. Many more people joined this field. Los Alamos with something like, so an improved version of the ANI neural net is shown here. The SCHNET neural net is shown here in gray. So you see such a data set allows us to compare all these different machine learning models and see where they land, roughly speaking. Now, some of these models are quite similar, some are very different, so it's not always a perfectly fair comparison, but it gives you a rough idea where the field is at the moment. Now, we think that this would be very helpful to further use this data set to improve models, and so we have a QM9 challenge. If one of the younger among you has a model that gets through this point, this set of professors here agreed to pay $100 to you. These data sets can vary, of course, and so if you change a data set, the question is, does the same machine learning model setup still perform that well? Of course, you still train on the new data set, but the framework, the architecture of the model is the same. And so here you see this FCHL for sidechain interactions, for water clusters, for elpastolite crystals, or materials in the open quantum materials data set. You will find more information on this in the original papers. They also work for different properties. I don't show this here. We can also work on data sets, and I'm going to gloss over this now, for data sets which do not contain atoms for which you wish to make a prediction. And also here you can get very good results. Now, why does this kernel approach work so well with one representation? It works better than with the other. A good way to visualize this is to do a principal component analysis of the corresponding kernel matrices. With the Coulomb matrix and the energy as a color code, you get for the first two components a plot like this. So you see a lot of overlapping, suggesting that a higher dimensional analysis is necessary to fully spread this out. With the Bob kernel, which is a little bit better, you see a clustering. So already this seems to be helpful for the machine. And now with the FCHL, just in 2 dimensions, you see a very smooth behavior across compound space. And this, of course, suggests that your regressor has to do much less of a work, that you effectively, the linear regression you do in this nonlinear kernel space is actually working. This is why it's working so well. Now, let me tell you about another paper very quickly where we managed to improve the slope in these learning curves. And this is a paper where, with my postdoc Bing Wang, we asked this question: if you have some large system, shouldn't there be a way to, rather than train a model on many other large systems, to simply train a molecule on atoms in the local environments, such as they occur in your large query model, and then stitch all these local environments together to have a scalable model that requires much less data and much more tailored data towards your query system. And this is what we call the AMAN approach. A and M stand for atom and molecule. And since these amens go through compound space, we appended the suffix on at the end. And so the idea is that when you have your usual kernel model, rather than measuring the distance between some query molecule and some amen training system, you say, I'm going to write this distance as a double summation over atoms in query and atoms in training. And now your training system, the number of atoms in your training can be much smaller than in your query. And so then you're only comparing the local environments when you train, and this works very well. And you can, of course, increase the local environment of your training system. And as you increase that environment, right, for instance, shown here for the water molecule, you increase that to methanol, to ethanol, to propanol, and every time you increase your predictive power, your error which you make on your query should come down. And this is something we can confirm. And so we think this is very much akin to a dictionary, right? As you would have a dictionary with words made up of letters, you can build up many different sentences and extract meaning. And so the amens take the role of these words in a dictionary. You make them up of atoms and you stitch them together to get a molecule for which you predict a property. So how does this work? If you have some query system, you have to identify the amens required for it. So we can run through this system with a graph searching or with a local environment searcher. And then we can identify the amen fragments that would make up this query system. And here you see all the amens up to size n equals 7. So n being the number of heavy atoms in the system, not counting hydrogens. And then you can look at the prediction error you make on this query. And this is shown here. Now this is the energy error you make. And you see it comes down as you increase the amen size. And then it goes below and then it comes up again. And the error you make is very, very small at the end for amen size 7. This also works for the polarizability shown here in red and many other properties I'll show you in a minute. Now, we wanted to make sure, of course, that there's not a coincidence. So you see here the mean absolute error over 11,000 such predictions. And you see that you very rapidly converge towards what's commonly known as chemical accuracy. And so how does this correspond to an improvement in slope here? Well, we can compare it to the models I just showed you before. And you see in particular here the FCHL learning curve for the same property, for the energy as well. And if we put the two in the same graphic, you see here the difference in slope between blue and black. That's basically how you speed up things by tailor selecting on the fly the relevant chemical environments rather than just drawing at random from a big pool. Now let me skip about some numerical results of this because time is flying by. So we tested this on many different systems. These are polymers, water clusters, sheets, silicon crystals, and now also for bio-organic molecules such as a peptide or even a protein. You can do hundreds of heavy atoms and get reasonable predictions in very fast time. Now let me tell you about a more theoretical approach where we wanted to exploit physics to improve the learning curves. In particular, in this paper with the Google people, we looked at various different properties, and what stood out was the dipole moment learning curves, and that's circled here in pink. And what you see here is actually that we had a neural net model that corresponds to this purple line, but it required over 100,000 training instances to get at some target accuracy. And none of the kernel models I told you about before came even close to that. And so we wanted to see if we can do something about a property like that. And in particular, we noticed, of course, that the dipole moment is the derivative of your energy with respect to electric field. And that relationship was not exploited in our training and learning procedure. So the question was, how can we introduce such a relationship, a differential response relationship in the machine learning model? And this is described in this paper, which was just published last year and was done by Anders Christensen, a postdoc in my lab, where we include response properties in the model. And so if your model describes your energy U as a kernel and a regression vector, regression weight vector, then some response property, omega here, would result from differentiating, from applying a differential operator on your energy or then on your model. And so you can use this now in your loss function for the training. So this is the training loss function. And you can rewrite this in terms of the expression below. And then when you solve for your alpha regression coefficients, you have to invert this kernel matrix and multiply it with this reference property, right? And so this is general. It's for any response operator, or you can think of so derivatives of any order with respect to any parameter. So for the first order derivatives in x and y and z, as you would need them for dipole moments or for atomic forces, you will find that you need to differentiate your kernels, as well as your reference property, of course. But you can also do this for second order derivatives or even higher. There's no problem. And this is how your regression coefficients will respond to this change in to introducing this relationship, which we know from physics. So a toy system where it becomes obvious that this is useful is shown here, the hydrogen fluoride molecule in varying electric field directions indicated by this arrow. The energy of the system calculated by MP2 is shown in red. If you don't have this response formalism, you provide this as a training point. Of course, your model doesn't know about this relationship. It will be invariant. If you introduce this differential constraint, then all of a sudden your model knows about it. And this point was fortuitously chosen such that it mimics pretty well the actual curve. Now on this QM9 data set, the improvement you get here is you go from the red to the blue, right? So basically you manage to get this green line here down towards the purple line just by introducing this differential relationship in your kernel learning. Now this works also for forces. It's very general. So here's the binding potential for HF. If you don't have the forces in your learning, your model will simply learn the best fit to the energies. That's this dotted blue one, and the dashed blue one corresponds to the same model but including the forces, and you see a much improved behavior. So we tested this also on other systems, and you can compare this to other systems in the literature. Quite recently, other groups introduced forces as well. And so a comparison to some results from the literature, the GDML model was published by my friends Tkachenko and Klaus Müller, but not with us. And so we compare our FCHL force thing to their GDML, and on average, the operator approach outperforms the GDML. We have a revised version, which is numerically much more efficient. And these are, with this revised version, the FCHL 19, we can get much quicker, very competitive results. So for more details, I refer you to the literature shown here. Also in terms of training time now, so this is something where potentially we could, with quantum algorithm, we could still speed up things considerably. So in terms of training time, this revised FCHL now requires this to invert these kernel matrices as a function of number of atoms in your training molecule. And the previous variant, so the state of the art is the blue one, and our previous operator was the black one. And in this revised version, the FCHL 19, we are much faster. Now, I'd still like to tell you about one more thing, how we can improve our machine learning models, and that is that we use previous results from worse methods, right? From methods that are less accurate, but that already that are fast to evaluate and that already encode some of the physics. And if you learn this difference, right, then you could ask, for instance, what if I have a DFT number? Can I learn the difference to QMC? And that should allow me to much faster get to where I want to be. And this is something which we explored early on in 2015 with my postdoc Raghu Ramakrishnan, who is now a reader at the Tata Institute in India. He worked on correcting baseline models with machine learning, and this is what we what's now known as the Delta machine learning approach. And he explored this in this JCTC paper to great lengths. What you see here now are different learning curves using different baselines in as baseline methods. And you see that the better your baseline, so this is semi-empirical, revised semi-empirical, GGA, hybrid functions, you see a systematic improvement in your learning curve as your baseline is improving. And this makes sense, of course, but in this paper, we were the first to demonstrate that this can be exploited numerically. And we show here now for all the 134,000 molecules in QM9, you see here the difference between semi-empirical and DFT methods. You see very large errors in many cases. So 30 kcal per mole is very, very considerable. If you train a machine learning model on just 10,000 examples shown here, the error distribution improves from yellow to this red. And you can now correct all the remaining 124,000 molecules and get very close to DFT accuracy in just for very modest CPU time investment. Such corrections can also be used to improve on, for instance, density functional theory approximations to intermolecular interactions. So van der Waals interactions are well known to be poorly described by machine learning. So this paper was just accepted in JCTC, where we corrected the various DFTs, and you see here that the correction allows you to shrink that error below chemical accuracy. We showed this for many cases. And then finally, I want to tell you that you can not only correct one method to the next, but you can also, more importantly, you can connect all sorts of methods. You can connect ensembles of different methods in order to minimize the necessary number of the most expensive training instances. And this is a paper which we also just published last year. We collaborated on this with mathematicians, with Helmut Habrecht, who is also at the University of Basel, and his postdoc, Peter Zaspel. And the technique is called the multi-level sparse grid combination technique. We dubbed it CQML. And it's basically a recursive machine learning model where you go through the space of possible methods, and you have different training set sizes coming from each level, and you connect it to the previous models by this recursive formula. It's actually quite straightforward once you set it up. And we saw, let me skip about on these, we saw a systematic improvement, as you can see here, for the learning curve without anything. That's the black one. You can get to the other learning curves by adding more of the lower lying levels. And you can do so systematically, reducing your cost. And in this case here, we did the full 3D scan. So basis set size, electron correlation treatment, and number of training instances. And you see we can get from the black towards this red one here just by connecting all these other methods. And what's shown here as training set size is the number of molecules required at the most expensive level of theory. And now you might wonder, why didn't we go all the way down to 1 here? And the reason is basically that we ran out of cheap of the lowest level methods, examples for the lowest level method. So this would have required over 25,000 Hartree-Fock molecules, and for this data set we didn't have so many, so we had to stop early. Right now we are working with my postdoc Max Schwilk on revisiting this and doing a much larger study on this. Finally, and this is the last paper I wanted to tell you about, we have here my student Heini, who is my PhD student in my group, and with him we looked at this question: if we can also not only predict some property, some physical property of a compound, but if we could also predict the CPU time required to solve Schrödinger's equation for a given molecule, for a given material. And you might be aware of this, but this is shown again here in this figure. You see here the performance in petaflop of the top 500 supercomputers, and it is estimated that roughly 1/3 of their CPU time is invested on problems coming from chemistry and materials, most importantly molecular dynamics and quantum chemistry calculations. And so if we were able to accurately estimate the necessary cost of computing for any given material, of solving Schrödinger's equation, we could dramatically improve the efficiency in queuing and scheduling of all these calculations. And so we first wanted to test this on a toy system. These are two well-known test functions, the Rosenbrock function and the Himmelblaus function. And we wanted to see if we can learn the number of steps you need to optimize these functions. And of course, this depends on the algorithm you use. So for different algorithms, such as Newton method, the BFGS method, or the Newton conjugate gradient method, we train machine learning models on the Rosen and on the Himmelblau function to predict, given some initial conditions, to predict how long it will take to converge to the minimum. And here you see the mean absolute error and number of optimization steps versus the training set size, and you see very good learning. And so if we can do this for simple optimizers, we thought we can also do this for predicting how long it will take in terms of CPU time for calculating quantum properties. Now, these are wall time distributions of various quantum data sets we have. SP is single points, GO is geometry optimization, and here we have also some radicals, single point calculations, or even transition state search calculations. So these are typical compute jobs in quantum chemistry. and Heine trained learning curves on the required flops for doing this, in particular for the QM9. So you see we can quite accurately predict the necessary flops. And he also did this for wall times, predicting wall times on the various data sets, and you see good learning curves for all of them. And these can be exploited to then, and we demonstrated this in this paper as well, to improve the efficiency of the scheduling. In certain cases, we can reduce the overall CPU cost of running an entire quantum database by 50% or so. More common though, as a typical reduction is 10% of your CPU cost, which can still be substantial if you have a large data set. With this, I'm coming to the end. I show here the homepage of the software package which we provide for doing such calculations. It's the QML code. The main developer is Anders Christensen. It's on the GitHub, and you're welcome to use it and also contribute to it. I hope I could convince you that these learning curves play really a crucial role in engaging and assessing the performance and the quality of the machine learning models we develop. I think this is not an evolution, but rather a revolution. Just consider the fact that we can control statistically the accuracy of these models, and consider the speed up we gain in comparison to costly quantum calculations. I think the three well-known pillars of science, consisting of experiments, consisting of theory such as quantum mechanics, consisting of numerical simulation, they are being augmented as we speak now. During our days, they are being augmented by another pillar, which is statistical learning, surrogate models and statistical learning. These are the members of my research group. I circled in pink those who really contributed to what I just told you about. I also want to mention that because of this field rapidly emerging and becoming so important, the Institute of Physics in the UK decided it should launch a journal trying to collect, not for the mathematicians, but for the scientists like us, to collect machine learning technical advancements. This is called the Machine Learning Science and Technology Journal, and I was asked to serve as an editor-in-chief, but the entire editorial board consists of people really coming from the field, so active researchers are running this journal. It was launched actually in January, and it's fully open access, and the article processing charges are waived until July 2020. So please consider this journal if you have something in this field to submit. And with this, I'm happy to answer any question, and I'd like to thank you for your attention.
Okay, Anatole, thank you very much for this really comprehensive talk. I think for most of the people was new of the audience, and this was really very, very interesting. Now I have to make an exercise. I will unmute everybody, and we would like to try to give you applause, nevertheless. So please go ahead. Okay. This is a function which is still missing in Zoom, obviously. And now to continue the question round. Am I right? Everybody should have a tool which is called raise hand in the participants list. Yes. I would like to ask that the people are using this. Okay.
Du coup, moi, j'ai essayé d'utiliser les routines Johnson. Le problème, c'est
Hello?
Yes, we're here, Mario.
Yes. Okay. There was somebody asking a question on English, yeah? On French. I would like to ask that we continue in English. Yeah? So, could you please use the raise hand tool that I can distribute the questions? Is this possible?
Maybe in the meantime, I would like to ask a question, if possible, Mario.
Yes, yes. Shannon, start.
So Anatole, thank you very much. It was a great talk. Even the technology seemed to work quite well, so I'm really pleased. In your talk, you mainly concentrated on molecular structure and energies. I was wondering also if quantum machine learning techniques can be applied to dynamics problems, and if, for example, the strategies are different fundamentally for quantum dynamics.
So I see two ways to tackle this. One is on the level of the potential energy surface. So this is very much along the line of what Eucor does and Gabosani, that you actually try to mimic a force field, but rather than having a force field, you have a machine learning algorithm. Okay, and so you train on data which you have for your system, and then when your system, then you use the machine to sample your configurational space, your phase space, with the machine as a force. The machine gives you the force to do that, but you would use your standard Verlet algorithm or whatever you do, or your Monte Carlo sampling scheme, or whatever you do, right? So this is one way, and that works quite well. So I showed also within our operator approach how we calculate forces, right? And so extending this approach across compound space is definitely something that becomes possible now. It hasn't been done yet. That you could, for instance, using this, you could run QML-based trajectories of many different materials in parallel, right? Because it's applicable throughout compound space. That particular application, such an ensemble run, hasn't been done yet, but it's definitely something where we have all the ingredients now together. The second strategy I find obvious is that you try to directly learn the outcome of a statistical mechanical average. So you could directly learn the distributions, and there are also machine learning algorithms which do this for given systems already. These Boltzmann generating functions, for instance, Frank Noy at the FU Berlin, he has some great papers on this. But this is also something that has not yet been done through compound space. So we have begun in my lab to do some of that, but in particular, we are using experimental data sets to try to predict, for instance, melting points or boiling points, right? So phase diagrams, these kind of properties. But the results are still not very not very convincing, and I think one of the underlying problems is that is a problem of representation. So as you know, some degrees of freedom are being sampled when you do your phase-based sampling. But the number of degrees of freedom that are actually being integrated, this is very hard to know. So this amounts to basically a coarse graining problem, where you say, okay, certain degrees of freedom, so typically conformational degrees of freedom are integrated out, but the degrees of freedom of your bonds, right, they are usually not, bonds are usually not broken, and so you don't need those. So this distinction, however, is not really clear. For instance, if you wanted to do reactive dynamics, you wouldn't know beforehand which bonds would be broken, and then you don't know how to represent your system. So I think this is an extremely interesting question, but to my mind, it's still very open.
Okay, thank you. One technical remark: the raise hand tool obviously is not available. Please switch on your video and raise your hand, and then I will give you the question. First, one question from my side. Going beyond bonds, is this the reason why you didn't include metals so far in this approach, or how it's can you treat electrostatical forces? Or?
Yes. So no, there's no. We also did metals already in other work. I just didn't have time to talk about this. There's no general restriction. In fact, metals are something we are currently looking into. I think they are very interesting. We have one FIS-REFLET from 2016 where we included crystals, including metallic atoms from only main group, but there are metals in there, and it works just as well. So I don't think that the methods, the machine learning knows about how we group elements, right? So as long as we do it properly, it's all the same for the machine learning models, right? Of course, your density functional theory might be worse for metals than for other elements, but that's something that the machine doesn't know about.
Yes. Okay. There was Thanasis you wanted to ask?
Yes, hello. So it's I think it's a related question. Just a clarification, because I don't know this method. So you mentioned that you have databases like QM9 with 130 something thousand compounds.
Right.
So these are compounds that you calculate their properties each time, or do you go to the Merck index and copy properties that are experimentally determined?
So yeah, sorry, I didn't clarify this before, and this is a great question. This QM9 data set results from a list of molecules that I mentioned earlier. It's this GDB data set. So GDB is a list of molecular graphs. It contains 160 billion molecules. It goes up to molecules with up to 17 heavy atoms, not counting hydrogens, only organic molecules. So from this list, we took the 134,000 smallest molecules, and they are all molecules with up to nine atoms. And we did density functional theory calculations on them, on all of those. So this, at the time, this data set was published in 2014. At the time, the CPU time investment was quite substantial. It took maybe 2 months on our university cluster. I think nowadays it's much faster, but it's definitely within reach. So I think for for many system classes and for many relevant properties, the generation of such data sets has become affordable for most research groups in the developed world, I would say. And you don't need quantum Monte Carlo numbers for all molecules in order to test the machine learning model, right? You can also use a much lower level method and just to test the machine. Yeah, and so we also have the melting points I mentioned earlier. They would correspond to experimental numbers coming, for instance, from compound vendors, right? So they often provide melting points or from literature database. So I presented results in my talk coming from based on data sets of various sources. But usually we use quantum chemically pre-calculated numbers.
So actually it's a follow-up to Mario's question. Since I don't know what's the situation with organic molecules, because mostly I deal with metal complexes, for which theoretical methods have problems accurately predicting certain properties. So the theoretically calculated properties, do they match the experimental ones? So are your data points actually describing the reality?
So I had at the end, I had the slide with the pillars of science, right? And so it's very important. I mean, this is an excellent point, and I don't think it can be understated, right? We have the experiment, which is our ground truth, which also has error bars and so on, right? And inconsistent results in various labs and so on. So it has its own problems, but that's the ground truth, right? And then we build theory on that. And then we do numerical simulation, right? And of course, when you do theory, you introduce approximations, which introduce a deviation from experiment. And then when you do the numerics, you will also have some deviation. And then when you machine learn, then right, it's like an additional layer. It's a new layer of sophistication, where you will only be as accurate as your reference data. So if you trained on experimental data, you will inherit the errors of the experimental data. If you train on DFT or Lennard-Jones, you will inherit the errors of that model, right? The machine is ignorant of a higher truth. It's just statistics, right? So whatever your reference data encodes as an error, the machine will inherit.
Thank you.
Okay. Matthias?
Hi. Thanks, Anatole, for the very nice and comprehensive talk. I had the impression at the end that you tried to convince us that basically no matter what you did, you added new type of descriptors or response functions and whatnot. It always helped to improve your convergence or your machine learning efficiency if you take away the unphysical potentials. Now the question is this simply the message you want to give us? As I said, that's worthwhile of doing this kind of work, which I think you don't have to convince us really. But are there cases where you actually you find out that actually some things don't match? That, for example, adding a response functionality to your machine learning actually counters a previous optimization, so to say, which you have introduced before, and that for some systems you find out that maybe you should not match two things to not actually spoil your learning efficiency.
Yeah. So thank you. This is also a great point. Of course, as many others, I'm also guilty of reporting only the successful outcome, right? And I'm giving my interpretation as to why I think they have been successful. Now, we have such examples where following this logic of adding more physics resulted in worse learning curves. And in particular, there is this case where we trained using the Coulomb matrix, so just 1/r. And then we said, well, just like in this Baumel paper I mentioned later, the 1/r behavior is not how the energy looks like. So we should have some binding potential, right? So why don't we put that on the off-diagonal elements instead of the 1/r? And sure enough, results got worse, right? And so we were really puzzled by this. And we think now that the reason is that you have the 1/r is a bijective function. It's monotonic. If you have a binding potential, that's no longer the case. And so then you're confusing the machine. It could be either value, right? It could be the one on your dissociative tail or on the repulsive wall. And so that introduces a representation noise, which makes things worse for the machine. So that's our interpretation of this observation. But it was also surprising to us to see how little is actually known in terms of formal applied math on how to improve these learning curves. I think it's partially also due to a culture in machine learning that the proofs I mentioned by Wapnick and others, they were given for very formal settings, an infinite training set limits, and these are in practice, we don't have that, of course, in our field. And so we have to explore and discover this by ourselves. So there's very little other help, right? So I don't know if our interpretation of or explanation of why this got worse, if that is the actual reason for why it was worse, right? But that's what I presume. So whenever you lose uniqueness in your representation, that's definitely a bad thing. And so if you introduce more physics at the expense of uniqueness, that's not necessarily a good move, right?
Okay, thank you.
Okay. Are there more questions, comments to Anatole? Maybe I'm allowed to maybe one concluding one. You have built your pillars of science around Schrödinger. What's about Feynman? Who stated to simulate a quantum system, you have to use a quantum system, a molecular quantum system in particular. How your approach, or what's your opinion to your position to this statement, to this thought?
No, so this is, I think so I use Schrödinger as an example. I think any one of these towering figures who introduced the physical framework on what we build could be used there just as well. What I find really attractive is the whole quantum computing, how that enters now in this picture, and how it could possibly be the next pillar, or it could make all these pillars become coherent. So this is something I'm very interested in, but yes. Yeah, I don't want to be quoted on insisting that Schrödinger is the one and only there.
Yes. Now, actually, we would enter into this QQ quadrant you mentioned.
Exactly.
You have shown.
Exactly.
But this we will do this afternoon, I think. So,
okay.
Okay. So if
right.
there are no other questions, comments, I would like to thank Anatole for the discussion and for the talk.
Thank you all.
Thank to everybody for making it possible. And we have this applause tool about reactions, so people can use this. We can't hear it. Huh? And there was only 1 or 2 freezing moments, huh? Where the image got stuck, huh? But I think this was quite successful and something to repeat in future. Huh? Thank you very much. So thank you, everybody.
Yeah, goodbye.
Goodbye.